Hello my dear students, in this video now we are going to study about the imidazole preparation and properties. So first of all we go for the preparation methods. Preparation or synthesis. Under that, the first method is preparation of the imidazole by using glyoxal. We can write the glyoxal reaction with the glyoxal like this. This is known as glyoxal. So when this glyoxal is treated with the ammonia, we get the imidazole. And the water molecules goes outside like this. Now we go for the mechanism of this reaction. In the first step, glyoxal undergoes hydrolysis. So we write H hydro on one side and hydroxyl group to another side. So whenever it undergoes hydrolysis, we get the formaldehyde and formic acid. This is formaldehyde and this is formic acid. Okay. In the second step, this formaldehyde reacts with ammonia and forms methyl diamine. So here methyl diamine, water molecule goes outside. As a result, we get the methyl diamine. This is known as the methyl diamine. Sorry, diaminomethane. We can call it as the diaminomethane. In the third step, this diaminomethane reacts with the glyoxal and we get the what is it? Imidazole ultimately. So here this is a condensation reaction and water molecule goes outside. So as a result, what happens? So this is the unstable compound and this one undergoes stoichiomerism or aromatization. As a result, what happens? Look here. So this bond comes here and this bond electron pair goes here and sorry, I have written in wrong manner. So this CH bond breaks here and electron pair comes here. This bond will be shifted here. Okay, right. Okay, no problem. And this bond breaks here and electron pair comes onto the nitrogen. As a result, what happens? Look here. So like this we get the imidazole. Go for the second preparation method of the imidazoles, that is the Radish Juski method. In a Radish Juski method, 1 comma 2 dicarbonyl compounds are allowed to react with ammonia or derivatives of ammonia. That means amine, derivatives of ammonia with aldehydes, whether it may be aromatic or aliphatic aldehyde. Okay? So for the 1 comma 2 dicarbonyl compounds we can take simple glyoxal also, but most popularly we write the benzyl for the 1 comma 2 dicarbonyl compound. So here we write the benzyl. So right, this is benzyl. Okay. Now in the first step what happens, ammonia molecules react with benzyl. So look here, this is a benzyl is 1 comma 2 dicarbonyl compounds. So as a result, first of all we get a condensed product. Okay, so this condensed product is known as diimine. So this condensed product is known as the diimine. In the second step, these diimines react with aldehyde like this. Now here for aldehyde we take here benzaldehyde like this. So look here. So here also water goes outside. So look here. Now this hydrogen undergoes tautomerism. As a result, we get the imidazole. So we write that as the third step. Okay. So now this bond breaks here, and this bond is shifted here. Okay, and this electron pair comes onto this nitrogen. As a result, what happens? Look here. So look here. So here, like this, imidazole ring is formed. So imidazole derivative. So this is imidazole derivative. Okay. So this is method is known as the Radish-Juski method. In a Radish-Juski method, starting materials are 1 comma 2 dicarbonyl compounds, ammonia or primary amine, and the aldehydes. So these are the materials that are used in the preparation of the imidazole by using the Radish-Juski method. Now we go for the third preparation method of the imidazole. And in this method we use the alpha haloketones and imidines as the starting materials. So look here, if it is the keto group, so in the alpha position we have to put one halogen. So for halogens we are writing bromine. So we can make it as ketone by keeping one alkyl group or aryl group. Okay, so this is now alpha bromo ketone. Okay na? So if you write here benzene ring, then what happens? Look here, becomes the phenacyl bromide. So name of this one becomes as the phenacyl bromide. So this is one alpha ketone, and here we have to use the imidine. So imidine structure is like this. So imidine contains one imine and one amine. So C double bond NH group is known as imine group, and NH group is known as amine group. So this is known as the imidine structure. So here we put methyl. So whenever we put methyl, it becomes the methyl imidine. So it is a methyl imidine molecule. Okay. So actually, in the first step, what happens means here this bromine and this hydrogen goes outside in the form of the hydrogen bromide, HBr, and this reaction is catalyzed by the base, because we acid molecule is removed, no? So to remove the acid molecule we require base. So HBr goes outside. As a result, we get the substituted product like this. Now, in the presence of base or acid, here this C double bond carbonyl group and this hydrogen of the amines undergo condensation and water goes outside. As a result, we get this unstable compound. Here, this carbon, two hydrogens are there, so we can take one hydrogen out. So look here, what is that? This bond is shifted here, and this bond will break here and shifts onto the nitrogen. As a result, we get the imidazole ring. Imidazole ring. Okay. So look here, this is imidazole ring. Okay, na? Imidazole ring. So like that, this is the third method. Okay. Now we study the physical properties. Under the physical properties, we study 2 points. First one is about the hydrogen bond, and the second one is of the tautomerism. Here, in imidazole, due to the formation of hydrogen bonds between the molecules, these molecules exist as the polymeric chains, whereas the pyrrozole exists as the only dimer. So we can say that imidazole's melting and boiling points are greater than the melting and boiling points of the pyrrozole. Okay, dimer, pyrrozole exists as dimer, whereas the imidazole exists as the polymeric chains. Okay, now we go for the tautomerism. Look here, tautomerism means shifting of the small atom like hydrogen in between the two positions of the molecular framework is known as the tautomerism. So here hydrogen shifts between the first nitrogen and the third nitrogen. That means first position to the third position. Okay now. So due to this shifting, both the structures become similar. As a result, what is that? The hydrogens present at the fourth position and fifth position behave in the similar manner. That means the environment around these two hydrogens becomes much similar. As a result, both these hydrogens give the NMR signal at the same chemical shift, that is the 7.14 and 7.14. Okay, and this hydrogen gives the signal at the 7.7. Okay na? So By this proof, we can say that tautomerism exists in the imidazole. Now we discuss about the basic nature of the imidazole. In imidazole, two nitrogen atoms are there, so that's why we can say it acts as the Lewis base. In the similar manner, pyrrozole also has two nitrogen atoms in it, so pyrrozole also acts as the base. Among these two, imidazole is the strong base. In both these pyrrozole and imidazole, on protonation, we get this type of resonance structures. In these resonance structures, nitrogen gets the positive charge in some resonance structures. Okay, in imidazole also we observe the positive charge on the nitrogen atom. Okay, na? Here in this structure and in this structure, positive charge is there on the nitrogen atoms. Okay, but in pyrrozole, two nitrogen atoms are present in the adjacent position. Due to this, the basic nature of the pyrrozole is less than the basic nature of the imidazole. And again, on protonation, one of these two adjacent atoms becomes positive. That means the positively charged nitrogen atom decreases the electron donating capacity of the second nitrogen atom. Here, the positively charged nitrogen atom and the free nitrogen atom are present in adjacent positions. Whereas here, the positively charged atom, nitrogen atom, and the second nitrogen atom are somewhat distant from away each other. So that's why the effect of this N plus ion on this second nitrogen is less in imidazole compared to the pyrrozole. So that's why imidazole is a strong base compared to the pyrrozole. Here we can easily understand this fact by looking at this data. Look here. Here ammonia pKa value is 9.2, hydrogen pKa value is 7.9, hydroxylamine pKa value is 5.8. So here in ammonia only one nitrogen is there, whereas in hydrogen two nitrogen atoms are there in the adjacent positions. So electronegativity of one nitrogen atom withdraws the electron pair of the second nitrogen atom. As a result, the basicity decreases. That means pKa decreases. And in hydroxylamine, oxygen is more electronegative than the nitrogen. As a result, the pKa value of the hydroxylamine still less than the pKa value of the hydrogen. Okay, so pKa value is directly proportional to the basicity of the nature. Okay, and here we can observe the pKa value of the what is that pyrrole, pyrrozole, and imidazole. Look here, pyrrole pKa value is 0.4, pyrrozole pKa value is 2.5, and imidazole pKa value is 7.2. That means imidazole is a strong base than the pyrrozole and the pyrrole. Now we discuss about the aromatic nature of the imidazole. In imidazole, four electrons are available from the two pi bonds, and one electron pair is provided by the one of the two nitrogen atoms. So now the total number of five electrons becomes six. That's why imidazole behaves as an aromatic compound. But in the cycle, only five atoms are there. So that's why we can say that imidazole is an electron-rich aromatic compound. It is more reactive and less aromatic than the benzene and pyrrozole. Benzene resonance energy is 36 kilocalories per mole, whereas the pyrrozole resonance energy is 29.3 kilocalorie per mole, whereas the resonance energy of the imidazole is only 14.2 kilocalories per mole. That means imidazole is less aromatic than even than the pyrrozole. This is so because in pyrrozole two electronegative nitrogen atoms are present in the adjacent positions to each other. So that's why it is more aromatic than the imidazole. In imidazole, two nitrogen atoms are separated by the 1 and 2 carbon atoms. Okay, um, and we know very well that aromatic compound shows the electrophilic substitution reactions. So imidazole also shows some electrophilic substitution reactions, and in imidazole, fourth and fifth positions are more susceptible for the electrophilic attack. Here, when electrophile attacks on the second position, we have the three hydrogen structures, but in all these three hydrogen structures, we can observe the presence of the positive charge on the two nitrogen atoms. Okay, so here two nitrogen atoms get the positive charge, and this looks somewhat absurd because nitrogen is more electronegative atom. Okay, and when electrophile attacks on the fourth position, two resonance structures possible, but here positive charge appears on the only one nitrogen atom. Okay, so that's why it is more feasible. Okay, and in when the electrophile attacks on the fifth position, again we get the three resonance structures, but only one of these two nitrogen atoms gets the positive charge. So this is also possible. That means in imidazole, electrophile attacks on the fourth as well as on the fifth positions. Okay, so now look here, these are some examples for the electrophilic substitution reactions: chlorination, bromination, iodination, and nitration and sulfonation. Actually, when imidazole and what is it reacted with chlorine, we get a mixture of different products. So that's why we can say that unidentified products here. And when bromine reacts with the imidazole at minus 10 degrees centigrade, we get the different products. Okay na? Among them, this is one. Okay na? So this is 2, 4 and 5, 2 comma 4 comma 5 tribromo imidazole. So its name is 2 comma 4 comma 5 tribromo imidazole. So here we have to use the very low temperature, and here this is highly substituted product. This happens because imidazole is less aromatic than the pyrazole and benzene. Okay, so with iodine in the presence of base, 2 comma 4 comma triiodo imidazole is obtained. When imidazole is treated with the fuming nitric acid and sulfuric acid, we get the either 4 nitro imidazole or 5 nitro imidazole. And when it is treated with the oleum, we get the mixture of the imidazole 4 sulfonic acid and imidazole 4 sulfonic acid, and this is 5 sulfonic acid. Okay na? A fuming acid, oleum means mixture of the sulfuric acid and the sulfur trioxide. Okay, now look here, imidazole shows the some nucleophilic reactions also, but actually the pure imidazole is less reactive or less susceptible to the nucleophilic substitution reactions. But whenever electron withdrawing groups are present, it may undergo nucleophilic substitution reactions. For example, look at this is pure imidazole. When it is treated with the alkoxide is a nucleophile. So look at, we can write chlorine here. This is one nucleophile and this is another nucleophile. So here nucleophilic substitution reaction does not take place. But whenever one electron with the dying group is present here, a nitro group is electron with the dying group. Okay na? So this chloride can be easily substituted with the alkoxide ions. So imidazole shows the nucleophilic substitution reactions whenever electron withdrawing groups are present in it. Okay, and when imidazole is treated with benzoyl chloride, this is a shorthand Bowman reaction. Okay na? short and Bowman reaction. Okay. Benzyl group will be substituted on the nitrogens, and this one easily undergoes the nucleophilic substitution, and ultimately it leads to the ring opening. And here what is that, we get the 1 comma 2 benzamidoethene. This is ethene, this is a benzamide, and two benzamides are there, so we can call it as the 1 comma 2. Okay, this is 1 and this is 2, and benzamide. So 1 comma 2 benzamido dibenzamidoethene, 1 comma 2 dibenzamidoethene. Okay, so nucleophilic substitution here leads to the ring opening. Now we go for the oxidation and reduction reactions. Generally, imidazole is very stable to the oxidation as well as the reduction reactions. So that's why here, look here, with any of the what is that, reducing agent, it is not showing any reaction. Okay, but here with strong oxidizing agents like hydrogen peroxide, look here, it is undergoing oxidation and forming oxamide. Okay, and under photochemical conditions it shows the some addition reactions also. So again, this is N-acyl imidazole and benzophenone in the presence of light, so we get a addition product. So here also we get a addition product. Thank you.